Okay, before we start with the actual talk, like always, I like to make a quick announcement. My name is Carsten Tellmann. I work for G-DATA Advanced Analytics actually, and I'm really happy to have my colleague here today to present some of his work. Like always, I like to invite you to our additional evening event, which basically is a 3-course meal with nice drinks and a cozy atmosphere. And the basic idea behind it is to offer you a nice platform where you have a relaxed atmosphere to discuss topics, maybe with others. If you have questions after the talk that are too complex or you want to discuss a little bit more in detail, we have plenty of time in the evening. Or if you like to get in touch with people working in the antivirus industry, especially if you want to talk to people more from the technical field, all of you are welcome to join us later. We will offer it again next week. I think when Markus is giving his last talk for this term, we don't have it anymore. So, yeah, I don't want to bore you anymore. So please, let's welcome Anders, our speaker.
Can everybody hear me? I've never spoken without a microphone before. Anyways, thank you all for coming here. Now that Carsten won't bore you anymore, I will take over. Thank you all for being here. The presentation that I'll be giving today is called Covert Shotgun, Automatically Finding Covert Channels in SMT. And we'll see if we can start that. This talk is about the microarchitecture of CPU and security. When I say microarchitecture, what I mean is that the architecture is what CPU vendors promise software developers. And the microarchitecture is how that architecture is implemented. So we'll be talking about how the architecture is implemented and the security aspects thereof. So this talk is not about software bugs. There will be no software in this presentation at all. It is often perceived that if we could fix all software bugs, we'll have secure computing. If the underlying hardware is in itself insecure, that assumption is not given. So this talk about how hardware design becomes an attack vector. And I'll be talking a lot about x86-64, and specifically a part of it, the so-called pipeline. What I want you to take away from this talk when we're done is a lot of beers at G-DATA, and that CPU design actually matters for security, specifically that the CPU leaks information, and that means that we can covertly extract information across security boundaries. This is what is called covert channels, and that covert channels are abundant in modern CPUs, and my personal opinion is that we'll probably have to live with covert channels in the future. So going into this talk, I was told by multiple people that most of you guys are web security people, and therefore I should not make it too complex. And since complexity is a minor theme in this talk, I thought I would start out with telling you what I think about web security. Chrome is 50 megabytes large. That's about 20 million instructions. Web security guys don't care much about Chrome because they have Safari, Edge, and Firefox as well. They run on operating system, Windows, iOS, Android. And of course, there is no web security without servers, databases, and it all runs on x86 and ARM and God knows what kind of computers. Well, doesn't work. Microarchitecture in comparison is relatively easy. This talk is about a dozen or so instructions only. There's no software and only x86. It doesn't work. So what could possibly go wrong? I'll only be talking about some 504 million transistors or so. Short, who am I? My name is Anders Fogh. I'm a principal security researcher at G-DATA Advanced Analytics. And the tweet by the Grok is there because I really wanted the Grok tweet in one of my slides at one point. So let's start out with some context and vocabulary. The security problem we'll be talking about today is the so-called confinement problem. And it is about how about trust inside a computer. There are many trust domains in modern computing. We have cloud computings. The logical question is, do you trust the neighbor in the cloud? We have multiple logins on single computers, and the logical question there is, do you trust the guest on your server? The web security people will already know that we have web pages that run code on your computer. Do you trust web pages that you visit? And you are all security people, so you should answer no. If you don't, you probably should get your money for the studies back. The solution to this problem is isolation. In cloud computing, we have virtual machines to isolate virtual machines from each other. On computers, we have the kernel that protect each login from each other. And on web pages, we have the JavaScript sandbox that will protect the rest of the computer from the browser. So Lampson in 1973, in Eternal Wisdom, defined the confinement problem, saying essentially it's really difficult to confine information when you're sharing a single computer. And inside of computers, we have three general ways of communicating. We have regular channels, side channels, and covert channels. And regular channels, we all know, they're there by design. Network, hardware drives memory, et cetera, et cetera. And we actually, by now, know fairly well how to confine them. Sometimes there's a bug, but usually it works quite well. On the left side, you see how the Windows XP, Windows 10 confines the files on the file system. Side channels. Here's an informal definition of what a side channel is. Side channels are side effects. That's actually part of the definition, meaning it's oops, they are in themselves a bug, so to speak. So define an operation O of P, where O is the operation and P is some private information. And let O of P leak some information, S, the signal. If the entropy of P is larger than the entropy of P given the signal, then S is a side channel on O for P. So let's unpack that a bit. If Alex encrypts a message, that will be the encryption will be the O. Using her private key, that is in this case the P. Eve is monitoring the power consumption, the S, of Alice's computer, and gains information about the private key from the power consumption. This is nothing more than the equation, the whatever math there says. So that escalated a bit quickly, so we'll take it a step down. Let me introduce Egon Olsen, my fellow Dane, cracking a safe using a side channel. The operation is turning the dial. The private information is the code for the safe, and the signal that he's getting is the noises that he's listening to with the stethoscope, and the inequality from before says that he has to be able to derive some information about the private key from listening to here. In this case, it's a very good side channel because Egon is able to open this safe cold. So, covert channels. The problem here is Alice has some private information P, and Mallory has a regular channel to P. She's able to read the file with the private key, say. And Mallory wants Eve to know, but has no regular channel to Eve. And the solution here is if Eve and Mallory know a side channel, Mallory can transmit P using the side channel. Having Mallory in the process is much less restrictive. You should probably think of Mallory as a Trojan or something like that. So even Mallory can now pick any operation that leaks any information. And Eve can then encode P in any data used by this operation. Lampson, who defined the confinement problem, suggested using the CPU usage to transmit bits. What he suggested was to use the entire CPU for a period of time, meaning that the other user would not get any computation time, and use that to signal sending a 1 bit. And to send a 0 bit, he would then not use the CPU for a similar period of time, and in that way, he could transmit information. You should probably remember Lampson here because I will be referring to him again. So what is a covert channel? I have a demo video somewhere instead of a picture of a Dane. It should be there. So on the left-hand side, you see a browser in the host in the host operating system. On the right side, you see a guest operating system. I'm recycling this demo here. It's made by Michael Swartz. We used it in our presentation at Black Hat Europe about DRAM. So in a second, we should start seeing how the right-hand side virtual machine does not have any network. So there's no network here. It's confined, which are not supposed to be able to talk to the JavaScript in a browser in a sandbox. And now we start the Trojan, and we start typing, and the information shows up on the left-hand side with a small bit of delay. So we're able to transmit information. Despite of isolation here, we have a covert channel. We could watch it all day long. I could, I love it. But I think we should just move on and get to drinking some beer. So that was a demo video. So what you just saw is no software box. There is no software box we used in VirtualBox. We did not use any software box in either Linuxes, and we did not know of any software box in the JavaScript sandbox of Firefox either. So no box here. We did, however, transmit data in and out of a confined VM. That is the cloud scenario I described before. And we transmitted data in and out of JavaScript sandbox. The channel you saw here is located in DRAM. This is the row buffer. I should not be talking about that today. The question here is, does the CPU leak information as well? And as I'm talking about it, you gather that the answer is yes. So just to recap the typical use of this vocabulary that we have now established is that side channel is typically used when S is correlated with some kind of juicy information P, say crypto keys, passwords, stuff like that, meaning that Eve does not need Mallory as an insider. Whereas covert channel is typically used when S is correlated with something boring. In Lampson's case, CPU usage, not very private information in that. Or somebody generated random numbers, stuff like that. In this case, Eve needs Mallory and a regular channel to get on the juicy information. We also use covert channel, the word covert channel, when we don't really know what the signal correlates with, and it could be, in some cases, something juicy. And this is how I use it in this talk, because I have very little idea about what the covert channels that I'll be finding in a moment can be used for. So covert channel trivia. The channel you just saw was 11 bits per second. That is more than enough to steal your credit card. It'll take your credit card about 5 seconds to extract. The fastest known x86 covert channel, by the way, created by Clementine Maurice, who spoke here last time, is about 0.5 megabit. And that's enough for 720p HD webcam video. I prefer to say it's about 8,000 credit cards a second. Covert channels are not just for information. You can actually run a shell, SSH shell, over covert channels, so you can do really good command and control as well. We have an idea about how fast a covert channel can be in order to be in a secure computer, because the US Department of Defense made a definition of a safe computer in saying that if a covert channel has a bit rate above 0.1 bit per second, then we need to audit it for the computer to be safe. Nobody is auditing covert channels in modern computers, and it's kind of staggering that we are 5 million times above that threshold. And personally, I also question whether safety means that it takes 12 minutes to steal your credit card. I certainly once left a browser open longer than that. So we're also talking about CPUs, and this is now starting to get technical. Most people see CPUs as a black box. You put an instruction in, and out you get some changed registers and memory, maybe some memory changed. It doesn't have to be that way, and that is what we'll be talking about now. But first, a bit of history, because I'm a history jock. The instruction set that we're using in x86 is actually from 1974, just like me. Here, the basic instruction set was introduced in the 8080 CPU, which was one of the very first integrated microcontrollers. 4 years later, in 1978, the x86 saw the light of day. And in 1985, the basic security model of the x86 as it exists today was introduced. It has changed and been updated. It actually been made a bit simpler. The basic security model is page tables, security ring levels. These things were introduced in 1985. It's kind of staggering to think that it's that old. In 1989, the CPU got a pipeline, and we'll be speaking a lot about the pipeline. The other feature that we'll be talking about today is the SMT, simultaneous multithreading, also called hyperthreading in marketing terms. And that was introduced in year 2000 with the Pentium 4. However, we will not be talking about history. We will be talking about current CPUs. And current CPUs started in 2011 with the Sandy Bridge. And the basic model that Sandy Bridge is built on is the model that is in all current Intel CPUs today, including Kaby Lake, up and probably beyond Kaby Lake. So before we start getting a bit of assembler talks, I want to gauge how fast I should run over the assembler part. So how many have assembler experience, disassembler, repra, stuff like that? Okay, so I can move over the assembler relatively fast. Just some trivia questions here. Anybody know how many instructions there is on the Intel x86? Anybody got an idea? Moritz, you know. Meg, I guess. Few hundreds. How many registers? Okay. The instruction count of Intel x86 computers are between 900 and 2,100, depending on how you count them. The average malware analyst sees about 50 to 200 instructions, depending on how what you count as an instruction. For the registry count, I have absolutely no idea how many registers there is in the CPU. It's not very well documented. But I've counted at least 130 on the most conservative way of counting registers possible. Your average malware analyst sees about 24 of those regularly. In other words, your regular malware analyst sees about 5 to 20% of what the CPU is actually capable of doing on a regular basis. And malware analysts are some of the only people that are actually working with assembly these days. It's scary to think about. So complexity revisited. Why am I talking about complexity? Well, when things get complex, stuff starts to break. If we don't understand stuff, we can't implement it correctly. And we have some complexity here. We have plus 40 years of development. We have 900 plus instructions on 130 plus registers. We have 504 million transistors. Maybe we can find something in here. So here we have the object of desire. This is a Sandy Bridge CPU and a die shot. And to the left, we have a graphics processor, which I'll not talk about. Down below, we have the shared L3 cache, which Clementine Maurice talked about in the last session. And to the right, we have the system agent and memory controller, which Clementine also talked about. I find it kind of interesting that the system agent is also called off-core or even uncore in official Intel documentation. Having 3 names for the same thing is always a sign of complexity, and I find that's kind of interesting. And what we will be talking about today is just one of these cores and what is going on inside of that, and only part of it too. So there seems to be unofficial CPU designer motto, and it is, if you cannot do things fast, do many things at once. And in the previous picture, you actually saw an example of that. That is that modern CPUs comes with multiple cores. That is because they can't build the cores much faster, so they just build more in. There are 2 other things that we will be talking about a bit in a moment. That is, modern CPUs are super scalar, which means nothing more that they don't execute one instruction at a time. They actually execute multiple instructions at once. The other thing is simultaneous multithreading. That is, running multiple threads in one core. So now we have reached the start where I introduced the pipeline. The pipeline is the central nervous system as well as the beating heart of the CPU. It is where instructions are decoded into commands for the rest of the computer. And it starts up above with the instruction decoder, which pulls some bytes from the memory system and decodes them into instructions. It forwards those to the renamer, and the renamer's job is to resolve dependencies so that we are able to execute multiple instructions at once. And finally, then we put them into the reorder buffer. The reorder buffer is strictly for bookkeeping. And then we put the instructions down in the reservation station where the instruction wait that an execution unit is ready to execute them. And down below we have the execution units, and we should see that some execution units are doubled, say vector logic here. We have multiple for shifting, have multiple for layer instructions, stuff like that, meaning that they can actually not only execute many instructions at once, they can execute identical instructions at the same time. So this is what makes the CPU superscalar. That is, we can execute instructions in all these execution units. They are highly specialized for purpose. So just a quick summary here. The decoder decode bytes into manageable instructions. The renamer sort out dependencies. The reorder buffer does the bookkeeping, that we can do many things at once. The reservation station schedules execution, and we have many highly specialized execution. These things are built to be superscalar. So introducing SMT, simultaneous multithreading. It's called hyper-threading in Intel marketing terms. Means that 2 or more threads are running in one pipeline. And in the x86 computer, there's typically 2 threads, so this is the case we'll be talking about today. So the problem with single-threaded execution is that we have many specialized execution units that are not being used with most software. Imagine having 1 thread. You're probably doing some bookkeeping, whatever, with integer instructions, and you're not using the floating points instruction on the vector logic or stuff like that, meaning you have execution units that are just idling around. Then we have a very interesting thing is that sometimes you have dependencies. Here I've written a bit of code that moves something from memory into memory and multiplies it by 4. Obviously, you can't multiply something with 4 if you don't know what it is, so you have to wait until the memory operation is done. Memory operations are normally extremely slow. Here, up to 200 clock cycles, the multiplication will take about 3. So in this case, the pipeline has to wait. We usually call it stall here. And the total consequence of this is that the pipeline usage may be as low as 35%, even though the processor is running at 100% and you're waiting for it. And to alleviate this, the idea is here to take 2 threads in one pipeline. As for the underutilization of the execution units with 2 threads, we have double the chance that we have something that fits in one of the idle execution units. As for the stalls, it is unlikely that a second thread will be blocked by the same dependencies as the first thread. From an economic perspective, it makes perfect sense because both threads actually share most resources. Same decoder, same renamer, same reordering buffer, same execution units. So only very little additional resources needs to be added for a processor to be able to run simultaneous multithreading, say the registers. In essence, we get 2 virtual cores for the price of 1. So economically, it's a good idea as well as performance-wise. And wait, what? Both threads share most resources. Think of Lampson, and you'll know why this slide is here. So let me unpack that for you. Remember Lampson 1973 had a covert channel. Lampson sent 1 bit by grabbing a resource, in this case the entire CPU, and he sent 0 bit by not grabbing the CPU. And we are sharing most resources between 2 threads here. It's not too difficult to find out that this sounds like that we could do the same stuff. So we only need to identify which resources are really shared and how we can grab them and not grab them, and figure out how we can tell the difference. You probably guessed it already. There's a timing difference. If some resource, some instruction has to wait for the other thread. And since we're just doing covert channels, we don't have to really care about what the private information that correlates with this because we can encode it into anything. So how do we usually find a covert channel? I call the process sniping. The usual way we do it is we find a subsystem and analyze it for covert channels of whatever we are looking for. And Clementine showed you how you could do that in the last session. So here's an example. You can find a cache somewhere in the CPU. You can analyze the cache and profit, and you have a covert channel probably. Why does this work? Because uncached data usually loads into the cache and throws something else out, and Eve can check if Mallory loaded or evicted something from the cache through latency, that is timing, because that's the point of caches, to alleviate timing problems. So the problem is that I'm a lazy guy, and I don't like analyzing caches, so I don't do that. The other way of finding covert channels is reading the manual. And here we have a snippet from the Intel optimization manual. It says, under heavy load with multiple cores executing RDC in parallel, it is possible for the demand of random numbers by software processor threads to exceed the rate at which the random number generated hardware can supply them. This will lead the RDC instruction returning no data transitorily. When I read this, I said, challenge accepted. The hardware generator here is the resource that I can grab, and I grab them by sending many RDC instructions, and I can check what happens by executing an RDC instruction and see if no data is returned. So I developed this covert channel, and being me, I found another covert channel and developed that and wrote a blog post about the two of them. What I should have done was that somebody concurrently found the same place in the Intel manual, wrote a paper for it, and went to a tier 1 conference on it. So if you find something like this in a manual, write a paper. It's a good idea. What I asked myself after having found these two covert channels is, can we do it differently? And the answer is yes. My idea was we point a shotgun in the general direction and do automated, with that I mean do automated trial and error. We don't try to snipe, don't try to analyze something, we don't read through the entire manual hoping that some nugget will be there. We just do automated trial and error, and 2 threads in one pipeline, as you probably know from the last slides, is an obvious target. So this is what I did. So how do I imagine doing a shotgun? Well, I use Lampson's technique. We start out with a list of instructions. We pick one instruction to send the 1-bit value. We hope this instruction grabs some shared resources. We pick another instruction to send the 0-bit and hope that this instruction grabs less shared resources. And how do we receive? Well, we pick a third instruction to receive, and if the time it takes to execute this instruction varies with the instruction that I'm executing on the other thread, well, then we have a covert channel. There is a thing here. It's quite difficult to see through it that 2 instructions arrive at the same point in the pipeline from 2 different threads at the same time. And to solve this problem, I just do a loop on the sender side of things, so I know which instruction is currently executing on the sender side of things. So here we have an example covert channel. What is measured here is the average latency of the instruction at RIX, 1, and the 2 bars signifies different instructions. This is the latency of the add instruction if we're running pause on the other thread, and this is the latency of the add instruction when we are running knobs on the other thread in a loop. So we see a clear difference, and this means that we are able to communicate because the add only takes this long when we are running knobs on the other thread. So in this way, we can find covert channels. But before we start, why is the pipeline a good choice? Couldn't I just snipe the pipeline? And it does kind of seem prudent to look at what the pipeline actually does. So if you wish to sleep or check your Instagram or whatever, now is a good time to sleep. I will make sure to wake you up. If you want to know why covert shotgun actually works, you should stay with me. Either way, you get to see the results in about 15 to 20 minutes. And Carsten, who invited you to G-DATA, promised me not to sleep because he actually did the longest talk ever in HackPra. So we'll start with examining what's going on inside the instruction decoder of the pipeline, the beating heart of the entire CPU. So the pipeline takes an instruction, which, funnily enough, have a different name once we're inside the pipeline. Now it is called a macro op. Again, same thing, 2 names. We have some complexity here. It takes a macro op as input and breaks it into one or more micro ops. Why does it do that? Because it's faster and easier to work with micro ops. We'll see in a second why. So here we have two instructions. The first is inc RRX. Inc RRX is RRX plus 1 and set some flags. And that is exactly one micro op adding, it is an arithmetic micro op with add and RX and 1 as parameters. The second instruction here, called keyword pointer, is a much more complex instruction. It first loads the contents in memory at the address of RX into a temp variable. Then it sets the stack pointer to the return address, the data at the stack pointer to the return address. Then it increments the stack pointer so to be able to do another subfunction. And finally, it does a branch to which means setting the new instruction pointer. So here we have 4 micro ops, but of interest here is to see that, that this micro op is the same as this, meaning that instead of implementing the 2,100 instructions, that is the more relevant number for the pipeline, we need to implement a significantly smaller number of micro ops and can do the macro ops based on these building blocks. The reality is slightly more complex, but you get the picture. I should have put that line on every slide that comes from now on. I didn't, just remember it. So this is what the instruction decoder looks like on the inside. We start out with the instruction fetch, which is where we pull 16 bytes from memory and push them down the rest of the pipeline. The next station is the pre-decoder, and the pre-decoder, sorry, that was instruction fetch. The pre-decoder takes the byte sequence from memory and turns them back into instructions, pushes them down into the macro queue below. At this point, it'll get kind of interesting because if we run into a branch instruction here, it will also flag that and ask the branch prediction. Why do we have branch prediction? Well, imagine we have a branch, then we need to fetch instruction from somewhere else. However, since this is just decoding, we don't actually know where the branch is going, meaning we have 2 choices. Either we can wait until the branch instruction is executed, or we can try to predict it. Intel have chosen the latter, and they try to predict where the branch instruction is going, and start executing from there. That means pointing the instruction fetch to the new address where the data needs to come from. This is called speculative execution because we actually don't know if we should execute it until we have actually executed the branch instruction. So this is what the branch prediction does. It tries to predict where we're jumping. Inside the branch prediction unit, there is a very small thing called the loop stream detector. It happens to be my favorite subunit of the entire Intel CPU because it has the coolest acronym of all, the LSD. The LSD has a job. If it finds a very small loop, it'll fit in the queue below. And instead of fetching more bytes from memory and pre-decoding them, it locks down this queue and lets it circle around this queue until the loop ends. This has a very nice implication for me trying to build a shotgun because it allows me to disconnect myself entirely from the memory subsystem, which is full of noise and full of ugly stuff that gives rise to covert channels. And I would no longer be able to say that my covert channels are in the pipeline. I could tell for sure where they're from. But using the loop stream decoder, I can actually say, hey, this pipeline is not doing anything with memory. Well, then we have the macro op queue. Queues are in there to make things more fluent in case there is a small delay in fetching stuff from memory and stuff like that. But they also works as caches, and we already saw that caches make good covert channels. However, I think that this queue is replicated for each thread. I don't really know. The Intel manual hints it, but it doesn't say so explicitly. I think it doesn't because will get kind of messy with speculative execution when speculative execution goes wrong. So I think this queue is doubled, thus shared fairly, and the other thread cannot influence, the threads cannot influence one another here. So moving on, now we have macro-ops, and now we need micro-ops. And we have three ways that we can decode a macro-op into micro-ops. The first is the tiny thing here on here. That is the microcode decode engine. Very complex macro-ops can be decoded here. This is very complex is when it's more than 4 micro-ops. This is actually done in software in microcode in the CPU. So this is actually coded. This is what you can change this unit by changing the microcode, by using a microcode update. The second option consists of 4 units that will always run in parallel. And we have a complex decoder, the yellow one here, that can encode one macro-op that consists of up to 4 micro-ops, whereas these simple decoders can only decode one macro-op to one micro-op. And on the right side, we actually have a cache of previously decoded things we can use. So we have these 3 ways of decoding instructions. And this is where it becomes interesting from my point of view, because here we have a bottleneck, a shared resource. The decoding, no matter from where the instructions come, micro-ops comes, we're not able to push more than 4 micro-ops per clock cycle into the below queue. So if this capacity here is not shared fairly, then we have a possibility for covert channels. Say if one grabs it completely, the other won't be able to decode instructions, and it'll have to wait. It all depends on how it is shared, and there is nothing nowhere on how it is actually shared. I don't personally really care because I'm going to shotgun it, right? I'm just going to do trial and error and hope I hit something. So I don't really care. I don't know. I think that this is a potential source for covert channels. Below we have a queue for micro-ops. Again, I think this queue is actually shared for each thread. It makes so much sense when you're doing speculative execution wrongly. So a summary here, the CPU fetches 16 bytes from the memory subsystem. It pre-passes them into macro-ops. It predicts the branches and decodes for the prediction. Predicted branches, we can use the LSD to rule out noise from the memory subsystem. And we have 3 ways of decoding into micro-ops. The throughput of micro-ops is limited to 4 clock cycles per second, and this is a possible source for covert channels. So moving on to the renamer. One of the things I thought of when I was a bit younger was that the EAX register has some special place in memory. That is unfortunately not true because register values are stored as pointers. And here you have a register allocation table, which is the pointer table, and that one points into a physical register file. By the way, that's a very cool acronym, RAT. The physical register file is where the values are actually stored. And we can have the RX pointing to this register, 1, 2, 3, 4, and the RBX and RCX pointing to the same physical register, so they share the same value. That means that if we do a move instruction and stuff like that, we can just change these pointers instead of copying 64 bits. Also, there is a large number of temporary registers here, and we'll see more about them in a second. So why do we do this renaming stuff? Well, the first is the CPU can use the extra space that we have here to optimize code. And the second thing is the CPU needs extra storage in case it does a rollback. Remember, speculative execution, if we took the wrong path, we'll need to roll stuff back. So why do we do renaming here? Here we have a sequence of instructions. It always uses RX. We cannot change the order of these instructions. We cannot do any execution in parallel. The memory instructions are extremely expensive in terms of clock cycles that they need to execute, meaning that we have a rather large total of latency if we did it this way. However, if we rename the RIX register like this, we can now do everything in parallel, and in fact the move memory, the load instructions that loads memory and stores memory there are 2 execution units for those. For each of those in the execution units means we can do everything in parallel that's on the screen, meaning that we exactly half the time it takes to execute this. So by renaming the stuff, we can make it go faster because we can do it in parallel. There's more stuff renaming stuff like if you have a move RX RBX instruction. Without renaming, we have to copy 64 bits. With renames, we can even sometimes completely omit this instruction and not use it. We can also cheat on common constructs. Those of you who have done a lot of disassembly have probably often seen the SOR RX instruction when the compiler needs a 0 for something, or the sub RX does the same thing. Without the renaming, we have potential dependencies which can cause a stall, and we have to occupy an integer arithmetic unit. With rename, we can recognize this construction and just rename it to 0 and rename the flags accordingly. For renaming, we are limited to the number of available spots in the physical register file. And the question here is there any covert channels hiding here? No, there's not. The physical register file and the RAT are duplicated between threads. They don't actually share them because you can't really share the same registers between 2 threads. But the renamer itself is probably not duplicated, meaning that it renames for both threads. And it is limited to 4 rename operations per clock cycle. So do we have covert channels? Well, quite possibly, but I don't really know, and I don't really care because I'm just going to shotgun it. So moving on to the reorder buffer. From now on, it'll start to go a little bit fast, but there's an animation at the end to hopefully make things a bit more clear. The reorder buffer is nothing but a FIFO queue. Micro-ops are pushed in by the renamer, and micro-ops are deleted once we are completely done with them. It's basically just bookkeeping. It stores information about the micro-op itself, and it stores information about what happened once the micro-ops are executed. That is the result of the micro-op and the exception status, if there is any exceptions caused by the micro-ops. And it helps us execute micro-ops out of order. And we'll see it in action in a second, as I just said. So the next step is the reservation station. This is where instructions wait. So this is a queue where all micro-ops that are waiting for execution is placed. And here they wait until an execution unit is ready, and that a matching micro-op for the execution unit with all dependencies resolved is available. Yeah? It's important that micro-ops have their dependency resolved, otherwise they, of course, cannot execute. So this is what happens, is show the code for what happens in the execution units. First, the extra instructions, the micro-ops execute, bringing out an exception if something bad happened, like division by 0, and a result if it worked out all right. If this instruction was a mispredicted branch, was not a mispredicted branch, then this information is stored in the reordering buffer, and all dependencies on this micro-op are updated using a broadcast on a bus. If it was a mispredicted instruction, we just flush the pipeline and throw out everything prior to this particular micro-op. Why do we do that? Well, because it was speculative execution, it was a mispredicted branch, we went the wrong way somewhere. So after that, we reset the decoder to the correct branch target and start all over again. So this brings us to retirement. This is when instructions die. When a micro-op at the end of the reordering arrives at the end of the reordering buffer and is marked as complete by an execution unit, we know that no branches before that was mispredicted, meaning that this instruction should really count. So if all the micro-ops in the macro-op is done, then we can retire the macro operation. If there was an exception, we flush the pipeline and raise the exception. If this is because an exception is essentially means that everything that comes after this exception should not be executed. We throw it away, even though it might already have executed. Otherwise, it commits. And the commit is essentially renaming a temp register to an architectural register that is our RX, RBX, and so forth. And the final thing that happens when a macro op retires is that all micro ops from the macro op is removed from the ROB, taking the next instruction to the head of the queue, meaning that once that is executed, we can retire that as well. This is how the CPU maintains the illusion of executing in order, despite of the fact that it's executing out of order. It's executing whatever is ready to be executed. So this enables exceptions to always be thrown on the right exception, and it updates only the architectural registers only when the instruction is really done. So to the animation here. No, sorry, it was a bit more about retirement. We don't know much about how retirement actually works in the current Intel x86 computers. I have found no documentation and no hints about how it actually works. In the past, retirement has been a limited resource. I think that it is linked into the same renamer as we saw before, and thus we have a limited resource. It was a limited resource in the past processes, so it's quite possible that it still is so. Is the covert channel possible due to that? I think so. I don't know. I don't really care. I point my shotgun and just try to hit something. So here we have the actual animation. So we have stopped the CPU at a time where a load instruction, which was at one time a MOV RX sum address, is executing in the load unit on port 3. That will be this one here, yellow. It is here in the reordering buffer, and it's yellow, meaning that it's in execution unit. We also have a macro op number 2. This is this one. It's a branch operation. It's also waiting for execution. We have a macro op 4 here. This would be this one, which is waiting for execution here. Interesting stuff about this. I don't know if you can read it. It is dependent on this load. And finally, we have 2 micro ops that have already been executed in the last cycle. These 2 increment operations here, which have no dependency as the others, meaning that they could probably be executed out of order. So this is the state of the CPU when we start this animation. And what is going to happen next is that the load instruction is going to finish executing. I'm going to assume that it's not going to throw an exception. So what is going to happen? We're going to resolve the dependency in the let's just see what's happened. Well, the instruction retired. The micro op resource was broadcast on the bus, which resolves the dependencies on micro op 4. It's now marked as resolved, meaning it can start executing in the next cycle. The last macro op of this macro op, of the instruction, we know this because it was the head of the reordering buffer, meaning that we can retire it. And since we have no exception, the temp1 register that it was using is renamed into RX, meaning that we could now see it in a debugger. So what's going to happen next is that the branch instruction waiting on port 0 and the add something to a temp register on port 6 can both start to execute in the next cycle. In this example, I have chosen that we have a mispredicted branch. So the 2 instructions start executing, nothing special there. They're moved into the execution unit, start executing. What is going to happen next is, of course, that both instructions is going to be finished, and the branch instruction will finish executing, and since it's a mispredicted branch, we'll see what happens then. Well, the micro op 2 turned out mispredicted, and this means that the pipeline is flushed. Everything before that in the FIFO queue of the reordering buffer was executed conditional on this branch being correctly predicted, meaning we just simply throw it away. It all used temporary registers. Just throw it away, we have a rollback. The correct branch target is then sent to the instruction decoder, and we can start all over again. So I did cheat a bit here in this introduction of the pipeline. There is a stack machine in somewhere. I've Covert Shotgun, the program I made for automatically finding covert channels, does not yet support stack instructions. I quite simply don't know how the stack machine works yet. We discussed a rollback for registers. There is, of course, rollback for memory as well. I didn't discuss that because Covert Shotgun is designed for the pipeline only and not for the memory subsystem. The memory subsystem has had a lot of attention, and most of the stuff that's going on down there had been sniped, a lot of it by Clementine Maurice, as you saw last time. There are also some advanced features like macro-op fuse and micro-op fuse. I cut those for time. It's really interesting technology, but just no time. So summary of the pipeline. There are possible shared resources that could be exploited for covert channels. Those are the micro-op decoding, the rename logic, the execution units themselves, and retirement logic. But we don't really know. We're going to shotgun it. So this is the point where Carsten can wake up. The rest of you as well, stop checking your Instagram. Now we get to the results. Well, why do we shotgun? That was one of the questions I stated before we started analyzing the pipeline. Well, each of the steps here in the pipeline are heavily interconnected, meaning it becomes really difficult for us to analyze them separately, especially in light of that we don't actually get to see what's going on in there, except when something actually retires. Also, things change in Intel CPUs. Allegedly, the decoder has become wider, meaning that it's capable of doing more instructions per clock cycle. So this affects not that there is covert channels, but how pronounced that they are and how effective they are. New execution units had been added. In fact, the pipeline you just saw is a bastard pipeline. It's the first part of it is a pipeline from Sandy Bridge, and the execution unit is actually from the Broadwell CPU architecture, because I already had that. I was kind of lazy as I did the graphs. So more execution units means less shared resources, meaning that covert channels will maybe disappear. We have added more ports in the reservation station, which also changes the things here. And all the buffers and queues you saw in the pipeline, they change their size. They typically grow larger. And there's all kinds of stuff like this. And then there is the thing, AMD does everything slightly differently. So if we can do something automated, it saves us a lot of analysis. Why is the pipeline a good target? Well, the thing is, we can use fixed parameters on the input because the execution unit rarely differs on what kind of the input is. Say, contrast that to caches. They use undocumented index, tags, and mapping functions, and are heavily dependent on the parameters that you use for the instructions. And that often requires multiple instructions to cause contention, whereas the pipeline, every instruction has the possibility to cause contention. Meaning that parameters outside the pipeline turns out to be really important, and inside the pipeline, only slightly so. Meaning that we can use fixed parameters, and fixed parameters had the advantage it reduces the search space to only just instructions. Why is the pipeline a good? Another reason for the pipeline being a good target is that it's easy to establish contention between security domains. The only thing you have to do here is get one thread running on another security domain than your own, and that is pretty easy because schedulers of operating system and virtual machines tend to use the threads as if they were a safe resource to assign to anybody. So that happens quite automatically, and you can actually cause it with if you do it right with software. The third reason is that the bottlenecks in the pipeline are relatively easy to fuss. Say sending a lot of knobs will put pressure on the decoder. Sending a lot of vector instruction will put pressure on the vector units, meaning we are very likely to get results by actually targeting the pipeline. So designing a shotgun, you've seen this slide before. We start out with a list of instructions. You pick one instruction from the list to send the bit 1. We hope the instruction grabs one or more shared resources. Pick another instruction to send a 0 bit, hoping that this instruction grabs less resources than the other. And then you pick an instruction to receive, and if the latency of the instruction to receive depends on the bit, the instruction you're running on the other thread in a loop, then you have a covert channel. Again, it's difficult to synchronize a single instruction. Solution is we'll loop the sender side of things for a period of time. So we start out with a list of instructions and just try all combinations of one 0 bit and receiver instruction and see what comes out of it. So that means that we have an awful lot of stubs to code, and we need an array of functions that we can call, not just a list of instructions. And the solution I did was I took a just-in-time assembler by using the Keystone library. So just cheated there, generated the stubs on the fly. When we do this kind of things, interrupt happens. Interrupts come from hardware and stuff like that. Hardware, timers, stuff like that. And an interrupt always flushes the pipeline, just like you've seen before, actually. And this adds a lot of noise to your measurement. My solution here was quick and dirty. I did 40,000 samples and just threw away the 5,000 largest latencies, saying, oh, they're probably interrupts, just truncate the distribution. It's kind of quick and dirty, but it gets the results done when you're working on a Friday night. So when is the difference that you see between two instructions enough to say that we have a covert channel here? My first approach was to do a statistical t-test with my 40,000 observations. That quickly turned really sour, because with 40,000 observations, very slight differences become statistically significant, and that, of course, does not apply that this channel is practical in any kind of way. It means that statistically, you have a covert channel. But even Mallory would be very upset with me if they were doing less than 0.1 bit per second, not even qualifying as a Department of Defense problem. So I changed my strategy for detecting covert channels. And what I did was say that the average difference between the two instructions, the two center instructions, has to be at least 1 clock cycle. That makes sure that it is likely that in small amounts of instructions to get a difference. And the second part of the criteria was that the average difference between the two instructions has to be larger than the standard deviation of the timing of the receiver. This ensures that we have relatively no noises. Actually, we can quantify how much noise that is. It means that we get the right bit 70% of the time. 30% of the time we'll be guessing wrong, so we do have noise. Most of the channels perform far, far better than this measurement, but these channels were actually usable channels. So this is my results, and you probably can't even read that. There's just quite simply too many of them. Actually, it's only part of my results, because when you do something like that, of course, you get results for every instruction on the list, combined 3 times through, right? So I summarized it for you. It turns out what really, really surprised me is that we have more than 50% of the combinations that I've tested actually turn out to be covert channels. So we can communicate with more than 50% of all communications. And remember, these are just those that I consider practical. So it's actually a lot more. I tested 1,700 combinations. I could have written a longer list, but I would have taken forever to analyze the results. It's actually something I'm working on. So many of the covert channels materialize themselves when we encode the 0 bit as a stall. And we can cause the pipeline to stall in two easy ways to cause the pipeline to pause is using the pause instruction. The pause instruction is really there to cause the pipeline to stall. It is used when you are waiting for an interrupt using a spin lock. You can pause, and it allows the processor to power down, stuff like that. So it's there to cause a stall. The RDC instruction, we talked a tiny bit about that before. The RDC instruction gets a random number from the random number generator, which is located in the off core. And the time it takes for this data to get back is relatively heavy. It's about 200 clock cycles. So if I'm sending just RDC instructions, eventually I will stall the pipeline. So we have here encode stalls like this. And then any kind of activity on the execution units would automatically grow faster because it gets the entire pipeline for itself. So we had a lot of instructions that had this pattern. A lot of covert channels that have this pattern, having the RDC pause instructions on the one side and doing something on the other. Another very pronounced channel was when we use instructions on both threads that collude in the execution unit. That is, there's only one execution unit available for this instruction. Say you receive with an op, receive with an add instruction, and send with an add instruction, then you have collision on an execution unit, and that generally tends to slow things down, whereas if you use a knob on the other thread, it doesn't slow things down. So we have these execution unit collision covert channels. Interesting, where there are two execution units for the same type of instructions, we do see covert channels, but they are a lot less pronounced. They are not quite as efficient. They would give rise to a lot less bandwidth, meaning that we're probably seeing other covert channels for those cases. So the summary here is the pipeline the way the pipeline is implemented gives rise to a significant amount of a manifestation of covert channels. I speak here of manifestations because we didn't actually find more than a handful of different places that could cause these covert channels, so I don't find it fair to speak of different covert channels and manifestations of the same channels. Obviously, the combinations of the things do matter. We can have a covert channel that is a manifestation of 2 or 3 or 4 of the things are found. So I like to speak of manifestations. It was no surprise that we found these covert channels. I hinted at it with my wait, watch, share most resources slide. It is kind of surprising that it's more than 50% of the things that I tested, and that's just the practical ones. Here you should, of course, be aware I tested the instructions that I found fun, so there's a bit of selection bias in here. But nevertheless, even in my test, we have more than 500 covert channels manifestations. So it doesn't really matter about the bias. We can say there is a lot, even with just what we know. So this is where I argue why we should call it manifestations. I just did that. Here, my private opinion is that we only have one root cause. The root cause is not how the pipeline is designed. The root cause is that we share the pipeline between 2 threads, meaning that SMT is the root cause of all these covert channels, and we should expect to see covert channels as long as you run SMT, even if you redesign the pipeline. So what kind of countermeasures are available for this? You can, of course, turn off SMT. In fact, some cloud providers already do that today. You could make a hypervisor or a kernel that doesn't schedule different security domains on the same core. Nobody does that currently. It might also be counterproductive. In a typical cloud setting, you have like 64 virtual machines running on the same hardware and say 8 cores or 4 cores. That wouldn't even be possible, right? As for software countermeasures, channel would lose speed if we restricted the access to an accurate timer, such as the RDTSC instruction. The problem here is, even if we restrict the accurate timer, we can still rely on law of large numbers and just do it for a bit longer. So it basically just lowers the speed of the covert channels. And we could try to detect individual manifestations using stuff like performance counters, but we are talking about individual manifestations, and manifestations matters when we try to detect them. And with more than 500 just in my small sample here, it seems like we're not going to get traction for that. So not only the covert channels that I found here exist, we know of many other covert channels. There is one in the branch prediction unit, there's one in the micro op cache, there's one in the TLB, in the data cache, the row buffer, the RDC, and so on and so forth. Covert channels are abundant. And it gets worse. There's a large installed base of CPU already. And the covert channels, as you see today, they're highly connected with design choices that hinges on performance. And we have a hugely complex CPU with 40 plus years of backward compatibility issues, meaning we're unlikely to get rid of covert channels. So There has been more sharing added systematically over the last 40 years. Inside the CPU, where we have the pipeline and SMT, we have the caches that have been added later on. We also have more security domain in computers, say cloud computing is a good example of it. Nowadays, every process has their own security parameter because you don't want the browser to messing with your password vault. So things are really getting worse since 1993 when this problem was first described, meaning the trend is really against us. The short thing here is we need to get serious about CPU design, or we're just going to have to live with covert channels existing. I would like to say that that is the final word that we can say about covert channel and SMT in the pipeline. It isn't. There is much more research that could be done on the pipeline and on the subject, and I'm actually working on some of the stuff. One question could be how many of these covert channels will translate into a side channel, would connect to something juicy. One could imagine spying on SGX enclaves, stuff like that. I don't actually know anything about that. I have not done any work on it. So for now, thank you, and I hope to drink a beer with you guys in a moment.